Now we discuss some properties of transpose. First property is transpose of A transpose is equal to A. And second property is A plus P transpose is equal to A transpose plus B transpose. Third property is K into A transpose is equal to K A transpose. Fourth property is A B transpose is equal to B transpose A transpose. The order of these two matrices will be reversed. This is known as the reversal law. Order of the matrices will be reversed. And fifth property is A, B, C transpose is order of all the three matrices will be reversed. So this will be C transpose, B transpose, A transpose. And sixth property is A to the power of M transpose is equal to A transpose to the power of M. That is, if you first raise a matrix to the power of M and then take the transpose, or you first take the transpose and then raise the matrix to the power of M, the result will be same. And there is a general note in all these properties that the matrices involved are all compatible. These two are compatible for addition, these two are compatible for multiplication, and so on. All the matrices involved satisfy the compatibility condition. The next topic is symmetric and skew symmetric matrices. First of all, we define symmetric matrix. Let A be any matrix, then A is said to be symmetric if and only if A transpose is equal to A. Or we can also define this in mathematical form as let A be equal to Aij n cross n. Then A is symmetric if and only if Aij is equal to Aj I. If and only if Aij is equal to Aj I. Now I take a very simple example. Let A be equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Now A transpose will be equal to, now this row will become this column. So this will be A11, A12, A13. This row will become this column. So this will be A21, A22 and A23. This row will become this column. So we get A31, A32, A33. Now this matrix is symmetric. A is symmetric if and only if A is equal to A dash. That is, if and only if this entry is equal to this. A11 is equal to A11 and A12 is equal to A21. A13 must be equal to A31. This entry must be equal to this entry. A21 must be equal to A12. We have already written A21 is A12. A21 and A12 must be equal. A22 is equal to A22. A23 must be equal to A32. So we get A23 must be equal to A32. And A31 must be equal to A13. A31 must be equal to A13. We have already got this condition. Now A32 must be equal to A23. A32 must be equal to A23. We have already got this result. So next is A33 must be equal to A33. So what we get is if and only if A12 is equal to A21, A13 is equal to A31, A23 is equal to A32, if and only if Aij is equal to Aj. So this is the definition of the symmetric matrix. So using these conditions we get A is equal to A11, A12, this is A12, this is A13. Now A21 can be written as A12. So this will be A12. This is A22 and A23. This is A23. And A31. A31 can be written as A13. A13. And A32 can be written as A23. A33 is A33. So we get this matrix. And what we note in this matrix is this is the principal diagonal. This is the principal diagonal. And what we note is A12 is equal to A12 and A23 is equal to A23. The entries situated symmetrical to the principal diagonal are equal. And this is equal to this. So entries situated symmetrical to the principal diagonal are equal. So we can say if A is any square matrix, then A is symmetric if and only if all entries symmetric to the principal diagonal are equal. All entries symmetric to the principal diagonal are equal. You can see the side sheet. Now next definition is skew symmetric. Skew symmetric matrix. Let A be any square matrix, then A is skew symmetric if and only if A dash is equal to minus A. Or in mathematical form, we can say let A be any square matrix of order n. Then A is skew symmetric if and only if I is equal to 0. That is, all the diagonal entries are 0. And second is Aij is equal to minus Aj, I not equal to j. If I is not equal to j, then Aij must be equal to minus Aj and Ai must be equal to 0. If j is equal to I, entry must be 0. Now I take an example. For example, A is equal to, say, let A be a general matrix of order 3 cross 3. Then A dash is equal to, what we do is this row will become this column. So we get A11, A12, A13. This row will become second column. A21, A22, A23. Third row will become third column. A31, A32, A33. So A dash is equal to this much. Now A is skew symmetric if and only if A dash is equal to minus A. If and only if now A dash is this much and minus A is multiply each and every entry of A by minus 1. What we get is, we get this matrix. Now these two matrices are equal. So what we get is, if and only if A11 is equal to minus A11, A11 is equal to minus A11, A21 is equal to minus A12, A31 is equal to minus A13, and here we get A12 is equal to minus A21, A12 is equal to minus A21. This is same as this, and here we get A22 is equal to minus A22, A32 is equal to minus A23, A32 is equal to minus A23, and A13 must be equal to minus A31. A13 is equal to minus A31. We have already written this equation. So next is A23 is equal to minus A32. A23 is equal to minus A32. We have already written this equation. And A33 is equal to minus A33. A33 is equal to minus A33. If and only if, now from this equation what we get is 2A11 is 0, and next equation is A21 is equal to minus A12, and A31 is equal to minus A13, and this equation gives 2A22 is 0, and this equation gives A32 is equal to minus A23, and this equation gives 2A33 is equal to 0. So from here we get A11 is 0, A22 is 0, A33 is 0, and A21 is minus A12. If we interchange the rows and column index, then we must get minus sign. A31, if we interchange 3 and 1, we get minus A13. A32, if we interchange them, we get minus A23. So using these results, we can write A is equal to A11. A is this much. So A11 is 0. And A12, let it remain as A12. Next entry is A13, and A21. A21 is minus A12. This is minus A12. A22 is 0. Now this entry is A23. A31 can be written as minus A13. A13. And A32 can be written as minus A23, and A33 is 0. What we are doing here is, when the row index is smaller, we are not changing the entry, and when the row index is greater than the column index, we are replacing this entry using these results. So A21 must be minus A12, A31, the row index is greater, so replace it by this. So what we notice, that when row and column index are equal, the entries are 0. That is AI is 0, and Aij, when j is not equal to I, Aij must be minus Aji. So A21 must be equal to minus A12. A31 must be equal to minus A13. If we interchange Ij, there must be a negative sign. So A31 must be minus A13, and A32 must be equal to minus A23. That is, Aij must be equal to minus Aj. Now this is the principal diagonal. these entries are negative of these entries. And this entry is negative of this entry. So what we notice is the entries situated symmetrical to the principal diagonal are negative of each other. The entries situated symmetrical to the principal diagonal are negative of each other. So we can also define a skew symmetric matrix as let A be any square matrix, then A is skew symmetric if and only if all entries on the principal diagonal are 0. That is, all entries ai for which row and column index is equal must be 0, because for diagonal entries I is equal to j. So all entries for which I is equal to j, they must be 0, and entries symmetrical to the diagonal entries are negative of each other. So skew symmetric matrix can also be defined as this. I have already illustrated this to you. One more example. A is equal to, what we do is first we mark the places of the entries. These are the places. All entries on the principal diagonal must be 0. This is the principal diagonal. So this entry must be 0. This entry must be 0. This entry must be 0. And if these entries are, say, this is A and this is B, then this must be equal to minus A minus B. Entries symmetrical to the principal diagonal must be negative of each other. If this is C, then this must be minus C. So you can write a symmetrical matrix as all entries on the principal diagonal are 0 and the entries situated symmetrical to the principal diagonal are negative of each other. Now I take up some questions based on symmetric and skew symmetric matrix. First question is, if A is any square matrix, then A plus A transpose is symmetric. A minus A transpose is skew symmetric, and A dash and A dash A are symmetric matrices. So first part of the question is, let P be equal to A plus A dash. This is the first part. Let P be equal to A plus A dash. Now we have to prove that P is symmetric. That is, P dash must be equal to P. So P dash is equal to A plus A dash dash. Transpose of A plus A transpose. So this is equal to, by property of transpose, this must be equal to A dash plus A dash dash. We know A plus B transpose is A transpose plus B transpose. So this must be equal to A transpose plus A transpose transpose. So this must be equal to A transpose, and we know transpose of A transpose is A. We know A dash dash is equal to A. So this is equal to A plus A dash, because matrix addition is commutative. So this must be equal to P, and therefore P is symmetric. And second part is, let Q be equal to A minus A transpose. Then Q transpose is A minus A transpose transpose. So this is equal to A transpose minus A transpose transpose. So this is equal to A transpose minus and we again use the same result. A dash dash is A. So this must be equal to A, and this can be written as minus A plus A dash, because matrix addition is commutative. So this is equal to minus common, we get A minus A dash. So this is equal to minus Q. This is equal to minus Q. Therefore, Q is skew symmetric. So Q is skew symmetric. And third part is, now we have to prove that A dash and A dash A are symmetric. So let us call this as, say, R. R is equal to A dash. So R dash is equal to A dash dash. So this is equal to, now we know AB transpose is B transpose into A transpose. That is, the reversal law is true. The order of these two matrices will be reversed. So what we get is A dash dash into A dash. So B dash into A dash. A B dash, we know A B dash is equal to B dash A dash. Order of the matrices is reversed. So this will be A dash dash into A dash. So this is equal to, now A dash dash is A. So we get A into A dash. This is equal to R. R is nothing but A dash. So R is symmetric. R is symmetric. And on similar lines, you can prove that A dash A is also symmetric. You can try it yourself. These are not standard results, but still you can remember them. A plus A dash is symmetric and A minus A dash is skew symmetric. A dash is symmetric. A dash A is symmetric. Try to remember them. In this question, we are given that A and B are symmetric matrix. A is symmetric implies A dash is equal to A, and B is symmetric, so this implies B dash must be equal to B. If A and B are symmetric matrices, then we have to show that AB is symmetric. That is, AB dash is equal to AB. AB is symmetric if and only if AB is equal to BA. Now AB is symmetric if and only if AB dash is equal to AB. And we know that AB dash is B dash A dash. Reversal law is true. So we know AB dash is B dash A dash. If and only if, now let this be 1 and this be 2. So from 2, B dash must be equal to B, and from 1, A dash must be equal to A. So BA must be equal to AB. That is, the two matrices commute. AB is equal to BA. If and only if A and B commute. Hence proved. Next question is, let A and B be symmetric matrices of the same order, then AB plus BA is symmetric, AB minus BA is skew symmetric. So what we do is, A is symmetric implies A dash is equal to A, and B is symmetric, this implies B dash must be equal to B. Let PB equal to AB plus B. We have to prove that this is symmetric, that is P dash is equal to P. So we find P dash. P dash is AB plus BA dash, and this is equal to AB dash plus BA dash. We know A plus B dash is equal to A dash plus B dash. So this is equal to, now AB dash is B dash A dash, reversal law. So this is B dash A dash plus BA dash will be A dash B dash. So this is equal to, now B dash is B because B is symmetric. So this is equal to B and this must be equal to A. Plus this is symmetric, A is symmetric, therefore this must be A. And B dash is symmetric, therefore B dash must be equal to B. And since matrix addition is commutative, we can write this as AB plus BA. This is equal to P, and therefore P is symmetric. Therefore P is symmetric. Now we prove AB minus BA is skew symmetric. Now in order to prove AB minus BA is skew symmetric, let this be denoted by Q. So Q is AB minus BA. So in order to prove that this is skew symmetric, we shall prove that Q dash is equal to Q. So Q dash is equal to AB minus BA dash. So this is equal to AB dash minus BA dash, and this is equal to B dash A dash, reversal law, minus this will, again we will use the reversal law, and this will be equal to this. So this is equal to B dash is B and A dash is A, minus A dash is A and B dash is B, because A and B are symmetric. So this is equal to, we can write this as minus AB plus BA, and we can write this as minus common AB minus BA, and this is equal to minus Q is this much, so we get minus Q. Therefore Q is skew symmetric. Therefore Q is skew symmetric. So we have proved the result. Prove that every square matrix can be uniquely expressed as the sum of a symmetric and a skew symmetric matrix. So let A be any square matrix, then we can write A as A is equal to 1 by 2 into 2A, and this is equal to 1 by 2 into A plus A, and this can be written as 1 by 2 into A plus A dash plus A minus A dash. What we are doing is we are adding and subtracting A dash. We are adding and subtracting A dash. So we can write A as 1 by 2 of 2A, and this is equal to 1 by 2 of A plus A, and we add A dash and subtract A dash. So what we get is, we get 1 by 2 into A plus A dash plus 1 by 2 into A minus A dash. And we have already done in a previous question that A plus A dash is symmetric and A minus A dash is skew symmetric. So we have written this as a sum of a symmetric and a skew symmetric matrix. We keep in mind that A plus A dash is symmetric and A minus A dash is skew symmetric. That is why we are writing this as half of this, add and subtract it. This is symmetric and this is skew symmetric. So this is the main idea in doing this step. So this is equal to, say, P plus Q, where P is equal to 1 by 2 into A plus A dash and Q is equal to 1 by 2A minus A dash. And we shall now prove that P is symmetric and Q is skew symmetric. So first we prove that P is symmetric. So P dash is equal to 1 by 2 into A plus A dash whole dash. So this is equal to, now we can take the scalar out from the transpose. So we get this into A plus A dash dash. Now A plus B dash is A dash plus B dash. We can take the transpose on separate matrices. So this is equal to 1 by 2 into A dash plus A dash dash. Transpose of this plus transpose of this. So we get 1 by 2 into A dash plus A dash dash is A. And since matrix addition is commutative, we can write this as A plus A dash. So this is equal to P. Therefore, P is symmetric. Therefore, P is symmetric. Now we prove that Q is skew symmetric. Q dash is equal to 1 by 2A minus A dash whole dash. So this is equal to 1 by 2 comes out and we get A minus A dash dash. So this is equal to 1 by 2 into A dash minus A dash dash. Dash of these two matrices separately. So this is equal to 1 by 2 into A dash minus A dash dash is A. This is equal to this. So this can be written as 1 by 2 into minus A plus A dash. Matrix addition is commutative. So 1 by 2 and take minus common, we get A minus A dash is equal to minus Q. Therefore, Q is skew symmetric. So call this as 1, this is 2, this is 3. Therefore, 1 implies A is sum of a symmetric, that is P, and a skew symmetric, that is Q. Therefore, A is a sum of a symmetric and a skew symmetric matrix. A is sum of a symmetric and a skew symmetric matrix. So we have written A as a sum of a symmetric and a skew symmetric matrix. Now we have to prove the uniqueness. That is, this can be done only in one way. Uniqueness. This can be done only in one way. That is, this representation is unique. So what we do is, let if possible A be equal to R plus S. where R is symmetric and S is skew symmetric. Skew symmetric. That is, let A be represented as a sum of a symmetric and a skew symmetric matrix in this way. So what we shall prove, that A is equal to R plus S is same as A is equal to P plus Q. That is, R is equal to P and S is equal to Q. That is, this representation is same as this. This will show that this representation is unique. So what we do is we find A dash. So A dash is R plus S dash. So this is equal to R dash plus S dash. Now since R is symmetric, therefore R dash must be equal to R, and S is skew symmetric, therefore S dash must be equal to minus X. Because R is symmetric implies R dash is equal to R, and S is skew symmetric, therefore this implies S dash is equal to minus S. Now let this be given a number 4 and this be given the number 5. Now 4 plus 5 implies A plus A dash is equal to 4 plus R plus S plus R minus S is 2R. This is 2R, and this implies R is equal to 1 by 2 of A plus A dash, and from equation 2 this is equal to P from 2, and 4 minus 5 implies when we subtract them we get A minus A dash, and this is equal to R and R cancel and we get 2S. 4 minus 5, you can see the side sheet. 4 minus 5 is this much, and this implies S is equal to 1 by 2 into A minus A dash, and this implies S is equal to Q. Therefore 4 implies A is equal to R plus S is nothing but equal to P plus Q. That is, these two representations are not different. Therefore this proves that A can be represented as a sum of a symmetric and a skew symmetric matrix in a unique way. That is, if we write A is equal to R plus S, then R must be equal to P and S must be equal to Q. We have shown this in this discussion. Hence proved. We take up the next question. In this question, we are given these matrices and we have to express them as the sum of a symmetric and a skew symmetric matrix. We have to express this matrix as a sum of a symmetric and a skew symmetric matrix. Let us denote this matrix by A. As we did in the previous question, we can write A as half of A plus A, and add and subtract A dash, we will get A plus A dash plus A minus A dash, and this can be written as this is equal to half A plus A dash plus half A minus A dash. This is equal to, say, P plus Q, where P is equal to half of A plus A dash and Q is equal to half of A minus A dash. Now A dash is A dash is equal to, interchange the rows and columns. This will become the first column. So 3, 2, 3, second column. 4, 5, 3, third column. 2, 4, 5. So this is A dash. So we can write P is equal to half of A plus A dash. This is equal to half of, now A is plus A dash. A dash is, so this is A and this is A dash. Now what we do is we add these two matrices, that is add the corresponding entries. So 3 plus 3 will be 6, 2 plus 4 will be 6, 3 plus 2 is 5, and 4 plus 2 is 6, 5 plus 5 is 10, 3 plus 4 is 7, 2 plus 3 is 5, 4 plus 3 is 7, 5 plus 5 is 10. So we get this matrix, and this can be written as half of this. Multiply each and every entry of this matrix by half. So what we get is, this is 3, half of this is 3, half of 5 is 5 by 2, half of this is 3, half of this is 5, 7 by 2, 5 by 2, 7 by 2, and 10 by 2 is 5. So P is equal to this matrix. So let this be equal to 1, and Q is equal to half A minus A dash. This is equal to half into A. Now write down A here. A dash is, and this is equal to half. Now what we do is we subtract the corresponding entries. 3 minus 3 is 0, 2 minus 4 is minus 2, 3 minus 2 is 1, 4 minus 2 is 2, 5 minus 5 is 0, and 3 minus 4 is minus 1. 2 minus 3 is minus 1. 4 minus 3 is 1. 5 minus 5 is 0. So we get this matrix. And this can be simplified into, now multiply each and every entry by half. So what we get is 0, minus 1, 1 by 2. And this will be 1, 0, minus 1 by 2, minus 1 by 2, 1 by 2, and 0. This is say 2. Now we have written A as sum of P and Q. P is this much and Q is this much. Now we will prove that P is symmetric. P is symmetric. What we do is we find P dash. P dash is equal to, how much is P dash? P is this much. So P dash will be, this row will become first column. So 3, 3, 5 by 2. This row will become the second column. 3, 5, 7 by 2. This row will become third column. So 5 by 2, 7 by 2, and 5. And this is equal to, now compare it with this. This is 3, 3, 5 by 2, 3, 3, 5 by 2, 3, 5, 7 by 2, 3, 5. So all the entries are matching. So this is equal to P. And Q dash is equal to, this is Q. So Q dash is, this row will become first column. So 0, minus 1, half. This row will become second column. So this is 1, 0, minus half. this row will become third column. So minus half, half and 0. This is equal to, minus is common, we take minus common, we get 0, minus 1, half. 0 minus 1 half, and this will be 1 0 minus half, minus is common. This will again become minus half, this will be half, and this will be 0. So this is equal to minus, and compare it with Q. All the entries are same. So this is minus Q. Therefore, P is symmetric and Q is skew symmetric. And therefore, we have written A as a sum of a symmetric and a skew symmetric matrix. Symmetric matrix is P and Q is the skew symmetric matrix. So this is the answer. So answer is